And just by way of introduction, if you're new to the group or don't know us or me or any of the folks who are going to be kind of presenting today, I'm Adam Shear. I am the Vice President of Applied Data Science at Recurve. And we're really trying to wrap our heads around modeling for individual buildings and making sure that we can use AMI data and hourly data and daily data properly, along with the right weather data and all this kind of thing, create an open source standard that can be used for pay for performance programs and to make these demand side resources as grid relevant as they possibly can be. And thanks for those of you last week who took on this meeting and who contributed. I was out on paternity leave, so I'm happy to be back. And so forgive me if I cover something today that you might have already seen because I wasn't at the last meeting. But we're going to just start off with an agenda here. And right off the bat, we're going to talk some logistics, and then we're going to get into a couple quick points of review, like what is the problem that we're really trying to solve right now, and what are the quantitative decision-making framework and tools that we're putting in place so that we can make objective decisions. And one of those tools that I think you've heard the term so far, but we're going to do a little bit of a deeper dive today and talk specifically about how we're formulating this for the Caltrack daily model, is cross-validation. And then we're going to talk about some progress and results. Then we'll have an open discussion and preview and feedback on next topics. As with all of these meetings, we have quite a bit that we want to talk about, and we want to get everybody's feedback and ideas. So we're going to do our best to leave time and space for some of those things. If you have a question, definitely raise your hand or interject. And if the discussion gets to a point where we kind of need to move along, otherwise we won't hit like the main topics, I'll make sure to move us along. So don't be offended if that's the case. We'll try to strike the right balance here. So looking forward to today, and I just want to start with a few logistical notes right off the bat. I know that there's been some issues with the Zoom scheduling and automations and calendar invites. So just want to extend our apologies for that. We're going to cancel the Zoom setup and we're going to schedule via Gmail from this point forward. So look for that via the typical communications that come out from this project team. And we're also going to get some dedicated logistical support. So we have a customer success team here at Recurve who specializes in handling, the logistics of customer meetings, client meetings, and we're going to devote some of those resources here for the Caltrack working group. We all try to do this on as low of a budget as possible for obvious reasons, because we're just kind of all volunteering here. But I think that we need some more organization to make sure that those things are running smoothly, and we have the people to do that here. So apologies if you've experienced any kind of odd scheduling behavior or haven't seen cancellations come through or haven't seen invites come through. We're gonna try to switch that up, make it work. So look for that to change here in the next week or so. And the next meeting we're anticipating having on February 7th from 1 to 2:30 p.m. So kind of same day of week, same time, 3 weeks from now. We've been considering a 2-week cadence or a 3-week cadence. And, to be just perfectly honest, a 2-week cadence is a little on the fast side for us at the moment, and for others who I think are looking to contribute, mainly because we all have other work to do as well. So, believe it or not, we do other things aside from like Caltrack model development. So just note these things. Apologies again if you've experienced any kind of weirdness on the scheduling side. We're going to try to remedy that. Okay, with all of that being said, let's get into the meat of it today. So I just wanted to do a quick review and remind folks of what problems are we looking to solve, why are we trying to solve these problems, and to ground this in actual data and results from the existing Caltrack model. So for those of you who have seen this a million times, just bear with me. For those of you who haven't seen it before, this will be new and very relevant. So what I'm showing here on this graph, the green data points, every one of those green points is the energy consumption in this case, therms, so a gas meter, for every day of a year. So there's 365 data points there, each data point corresponding to a day. And the x-axis is the average temperature on that day. And the y-axis is how much gas this meter used. You can obviously see a pattern here where when the weather gets colder, energy usage increases. And when the weather gets warmer, it sort of stabilizes and there's a semi-linear region, or like a flat region to be on the right side of the graph. Now, if you kind of, this looks pretty reasonable, right? But if you squint, you can start to see some issues here. If you look out at the right side of the graph, for example, you can see that the model is tending, the model is the red line. That model is tending to over-predict consumption. If you look right around that balance point temperature, the model is tending to under-predict consumption a bit. And so this is the model formulation, is to have a temperature independent region, a balance point temperature, at which point there's a linearly increasing model that is on the left side of the graph. And that model is basically takes into account, how much does energy consumption increase as a function of temperature, and it's a linear model. Now, the CalTrack model, the daily model itself, has these 4 distinct formulations, and all of these formulations are tested for every meter. And ultimately, the model that we select is the one that serves that meter the best. So it's the best model fit, taking into account adjusted root mean squared error. So taking into account the degrees of freedom, for those of you who are well versed in these things. So every model is tested across these 4 types of profiles, and then the profile that best fits that model, leads to the lowest root mean, adjusted root mean squared error, is selected as the CalTrack model. So the basic components of the CalTrack daily model is that there is an intercept term, there is a heating balance point, a heating slope, and if you have an electric meter, then we also allow for a cooling balance point and a cooling slope. So the balance point temperatures are determined by a big grid search and where the model is best fit relative to where you assign that linearly increasing region after the intercept term. Those are the balance point temperatures, and then the slope are the beta terms, these parameters on the linearly increasing regions of the model. So what we found is that when you restrict the model to these parameters and these functional forms, that you wind up with some definitive sources of error. And those sources of error, this should be reviewed if you've been here in the last few weeks. One is weekdays and weekends. So the CalTrack model does not differentiate between weekdays and weekends. The CalTrack model does not differentiate between seasons. So summer months, winter months, there's no distinction made between those months. And there's thermal inertia effects. So if yesterday was very hot and today is very hot, you can get a different degree of cooling energy consumption versus if yesterday was mild and today is hot. So by only using the day of temperature, you are blind to those kinds of effects, and your model is prone to error along those types of impacts. And then finally, I've added one here. Restricting the model to linear functions it does not enable the model to match some of the nuance, especially around those balance point temperatures, where what we see in most meters is that linearly increasing function doesn't do a good job of fitting what is actually a much more gradual onset of heating or cooling. And so you get this linear model that's actually trying to fit something that belongs to a different functional form. So these are the main sources that we've seen, and I just want to give a few examples to show you why we're highlighting these specific elements. So this is a graph that shows an electric meter, and again, we have 365 data points on this graph. Again, the x-axis is temperature, the y-axis is consumption, and every blue data point is the circles are weekdays, and every green data point is a weekend. I think it's pretty clear that the CalTrack model itself, which is the orange line, is doing its best to strike a balance between the weekdays and the weekends, but it's really never doing a good job of fitting either. So by splitting the difference, it kind of is just erroneous on both sides. And this is kind of an obvious thing, right? If you have an office building and you're open 9 to 5, Monday through Friday, and then you're closed on the weekends, you're going to get, potentially this kind of behavior. But I actually want to show something else that results from this kind of a model design, which is if I actually look at the blue data and I just eyeball this and I say, well, what is actually the slope of the heating and cooling? Well, on the cooling side, that slope, to me, it looks a lot more like this. And I haven't fit this. This is just me eyeballing it. So take it for what you will. But it sure looks like the cooling balance point temperature that you can see out there around 78 degrees or so. Number one, it's too high. And number two, the slope that then the beta coefficient is too severe. Whereas on the other side, it sure looks like now the heating balance point is actually too high in the model and the slope is too shallow. So actually by having weekend and weekday bias or the model unaware of weekdays and weekends, we get these kinds of effects that kind of monkey with the temperature dependence of the model too. And in a very clear example of that is this meter, where now the circles are the weekdays and the diamonds here are the weekends. And the original CalTrack model or the CalTrack 2.0 model is this black curve. And if I'm just eyeballing this and looking at the weekdays, looking at the weekends, it's very, very clear that there's really not a temperature dependence in this meter whatsoever. But because the hot days in this case have occurred on the weekdays, the model trying to split the difference between the weekends and the weekdays ends up assigning a balance point temperature in a pretty significant slope. And so this is obviously an issue. So one of the things that we're going to be talking about is weekdays and weekends, and that being a source of bias in the model, and how we can remedy that with additional parameter to distinguish between weekends and weekdays. I'm going to just get through a few more slides and I'll stop for questions. So another source of bias, and this just connects back to what I was mentioning earlier, is seasonal bias. So the summer months are shown in the middle in red. The winter months are in blue on the right side. And if that's all you're looking at, that's fine. But I've also included the shoulder months, spring and fall in green. And the x-axis in each of these panels is now the average temperature of the day in question minus the heating balance point temperature. These are all gas meters, and this is a large sample. So this is aggregated statistics over something like 85,000 meters that we're looking at right now. And if I just look at the winter, so I'm looking at those blue curves on the right, I can clearly see that around the balance point temperature, which is this shown by this dotted vertical line, I have a very obvious error profile where the model, which is this solid curve, is under predicting the energy consumption. And it's doing so specifically around that balance point temperature. And then if I look at the summer and the shoulder, I get the opposite effect, where I'm now over predicting around the balance point temperature in both cases. And I get these very distinctive error profiles. So the top panels are the error profiles of the models. So in the winter, I'm just blowing up the difference between these two curves, the model and the observed. So overall, I'm under predicting in the winter. I'm over predicting in the summer and in the shoulder. And I also have this error profile that is the result of a non-linear, a more gradual onset of cooling or of heating in the winter, and a more gradual onset elsewhere throughout the year that we're trying to match with linear terms that just don't quite fit. So those are kind of, exhibit B, exhibit C kind of thing. And then finally, we have thermal lag error. So I have now this on the x-axis, I have the previous day's temperature minus the modeled day temperature. So if it was colder yesterday than it is today, then I'm on this side of the plot. And if it was warmer yesterday than today, I'm on this side of the plot. And if I'm just looking at the winter here, these two panels over on the right, again, the model is shown in with the solid line, and the actual observed data are shown by the data points. I can clearly see that if it was colder yesterday than today, the model is under predicting. And again, this is a gas meter. So that's basically saying that if it was colder yesterday than it was today, by and large, customers are using more energy than a model is predicting if it's only aware of today's temperature. So we're seeing these definitive areas where we can quantify error in the model. And the solutions that we're looking to describe are deliberately attacking each of these areas of bias. And so let me stop there, because then we can talk about kind of solutioning. But I want to make sure that folks are on the same page with what the sources of error that we're discovering are in the existing formulation of the CalTrack model. And then we can move on to other topics. So let me just stop to see if there are questions or thoughts or ideas.
Hey, Adam, it's Will Franklin from Energy Hub. I was just curious, at present, what are you defining as sort of shoulder versus in season for California?
Yeah, good question. So I'm really basing that on what type of, or when in the year you have the mildest temperatures and when you have cold and when you have hot months.
Gotcha.
And there's also a few things that factor into this, like time of use rates. So the winter months we're defining as November, December, January, February. The summer is June, July, August, and September. And then the shoulder months are March, April, May, and October. And that's maybe not perfect because, maybe you could say, well, the first half of November is a little bit more mild and maybe the first half of March is a little bit colder. These are things we can tweak. Mm-hmm. But in order to just elucidate these error profiles, they're definitely serving their purpose right now. But these are certainly things that we can tweak. And also, I think your point is making me also recollect that, if you're talking about Australia, you have a totally different summer and winter.
Right.
So, you need to be able to define what these time periods are in order for your model to latch on to the right things if you're including seasonal parameters in a model.
Yeah, and I think even within California, you've got some very different climate bands there. So
that's very true. So one of the things that Travis here at Recurve has done, and you'll hear from him a little bit later today, is to just do some very preliminary testing on how you can actually take an individual meter and look at 365 days and understand when you're actually starting to see seasonal patterns change in their energy consumption. And so that's something that's kind of on the table for us. And it is kind of gets back to like, how complex are you willing to make a model? That's not something that interferes with a model formulation once you've determined it. And there are good ways to kind of dive in and look for a mathematically driven way to actually define on an individual meter basis, like here's where we're starting to see patterns change relative to seasons. So if that's of interest to folks, I think that's something we would love to get people's input on, is like, or have other people seen that, or are there algorithms you've used? Or we can also kind of show what we've done and see if people feel like it's worthy of fleshing out further, if that would be of interest.
I won't go into too much detail about it, but more recently I've been looking at basing the seasons off of temperature data alone. One of the primary advantages to this is that, one, you don't have to put in what months you believe belong to which season, but two, when you flip that around, it means that you can run the model here in the Northern Hemisphere and in the Southern Hemisphere, and it would work without any changes at all.
Thanks, y'all.
Thank you. Very good. Yeah, very good question. Thank you. I see Kobe has his hand up. Kobe.
Hey Adam, Kobe Rudolph, CPUC, and I was curious, and if this is kind of too long of an answer, then just feel free to punt it, and maybe we can connect offline. But I was just curious to kind of get a sense of like when you guys look at these issues of error and bias, are there like certain thresholds that you're looking to kind of correct to, or like, you know, in other words, like how do you, I know you're going to kind of walk through some of the possibilities, you know, options for how to address these, but like how do you know if you're achieving the level of success that you want to achieve? Yeah.
Good question. So there's a whole bunch of other panels of this graph here that I haven't included just to keep us sane. But one of the panels is percent error. So when we're looking at like there's the average daily error in the winter for a residential gas meter in the sample is 0.14 therms. I forget what exactly the percentage is, but this is something like 15%. So we're seeing roughly 15% seasonal bias in the winter using the Caltrack 2.0 model on gas meters, on res gas meters. And similarly, you know, we see 0.07 therms here and 0.07 therms in the shoulder. And so in summer shoulder, we see 0.07 therms, which it's not a coincidence that these numbers add up to 0.14 therms and 100% cancel out this error term. So over the course of the entire year, the model is not biased on account of seasonal bias. It's just biased within the seasons, which can be a problem if you're paying month by month by month, right, on a pay for performance program as an example. And we use comparison groups to remedy these kinds of things, and comparison groups, if they're selected properly, do remedy these kinds of things. But you don't want to rely on a comparison group to fix these kinds of things if you can make a model that performs better. So to your question, we're seeing, say, 15% error in the winter. I would love to get that number as close to zero as possible. I can tell you that if it's above 10%, you know, I would not say it's successful if it's above 10%. I would not say it's successful if it's above 5%. Now, if we get down to 2%, maybe we're in the ballpark of like that's acceptable. So I don't have a specific number for you. Like it has to be under 2.5%. I mean, maybe as a group, that's something we can talk about. But what it comes down to ultimately is there is a balance to be had. And this is exactly what we're going to be talking about for a chunk of this meeting going forward is how do you actually reduce bias in a model without actually making the model so complex that it doesn't actually become predictive on like reporting period data as an example. So, you know, there is a balance to be had there, but I would say I'm very hopeful that we can get these numbers under like 5%, easily under 5% error on the seasons, just for example.
Thanks.
Yeah. I see Glenn has a question.
Yeah, hi, Adam. Thanks. This is Glenn from PG&E. Not exactly sure where I'm going with this, but I'm wondering if the degree to which these biases or errors are interacting with each other. I mean, is it possible that we're kind of viewing the same bias in a different view? For example, restrictions in the linearity.
Yeah, it's funny.
Maybe it's the same problem as this what we're looking at right now.
Yeah.
Does that make sense?
I'll tell you with confidence that seasonal bias is not thermal lag bias. We have definitely looked at that. I just haven't put together like a sexy graph or statistics, but I can tell you what, let me come next meeting with an example of this.
Okay.
Yeah, because it is not, these two things are, if they are correlated, they are only lightly correlated. You can have thermal inertia bias even when you don't have seasonal bias necessarily, and vice versa.
Yeah. Okay. That's great that you already looked at it. I just noticed the biases are right around the balance points And I'm where the two views. And anyway, I'll stop there. Thank you.
Oh no, it's so I'm looking forward to presenting this. Actually, I'm glad you're giving me an excuse to present something that I've kind of had in our back pocket and just didn't want to like cloud the issues too much. But
Sure.
For instance, if I look at like a day that's say 5 degrees colder than the balance point temperature, and yesterday was 5 degrees colder than today, right? I can isolate, this is a huge data set, so I can isolate those kinds of things and still have a lot of statistical power. And you can see the multiplicative effect that those sources of bias have. You get much worse bias when you have those kinds of overlapping effects.
Right, right. Okay, great. Thank you.
Yeah. Cool. I'm going to move us on, and we'll create time for more discussion here, but really good thoughts on everybody's part. So, okay, so what's the solution here? There's a whole bunch of things that we could add to a model. Right now we have an intercept with heating and cooling balance points and slopes, and obviously we can add week and weekday awareness. We can add seasonal flags. But why stop there? We could add additional weather data. Humidity may very well affect energy consumption, wind chill, or how about building information like what's the SEER rating of the air conditioner, or what's the thickness of the insulation, or water heater characteristics, nonlinear terms. There's a whole bunch of roads we could take in formulating a model. So just keep this in mind. It's just to say there are many options, but obviously, I think if the Caltrack 2.1 daily model ends up looking like this, we haven't really solved the problem. And it's not just that we haven't solved the problem because it's too complex. What I'm going to talk about in a minute here is like, no, we really truly haven't solved the problem if the model looks like this. And here's just kind of a comic that I found that was a little bit illustrative, the self-operating napkin. This comic was from 1932 in the New York Times or something like this. It's now public domain, so I have not referenced it. So let's come back to these decision-making principles, because ultimately we want to have a quantitative framework to make decisions and gauge model performance. So just in this blue box, I've kind of highlighted what we're really going to drill down on today. Model error, overfitting, simplicity versus complexity. Travis is going to talk about computational expense, because if a model gets kind of too complicated, then it becomes very expensive to run. And it becomes, really time consuming to run. And the wheels just kind of fall off for those reasons. And so we're going to focus in right now on like the trade-offs that we see between model error and simplicity versus complexity, and how we actually have a quantitative framework, and we've put in a sampling scheme that gives us like very clear source of truth results that are internally consistent with one another. So underfitting and overfitting, these are concepts that are common to modeling. And so if you've been heavily involved in modeling building data or performing other kinds of models, these concepts are probably very familiar to you. If you haven't, I hope you learned something new here. I have to say, even like I've learned something new in researching some of this stuff of late. And I just have a big example here I'm going to walk through. So let me just take a moment and explain what you're seeing on this slide. So what we have done is taken a data set, and this is one model. This is 1 meter. So we've taken 1 meter and we've split out into 2 data sets. And one data set we're going to use to train a model. So we're going to fit a model on one data set. And we're showing that the observed consumption of this meter that is in the training data set is shown by these blue stars in the top left panel. So again, we have temperature on the x-axis and we have consumption on the y-axis. And the bottom graph, the open circles, are a testing data set. So the model itself is fit on the training data. And then we then apply that model to the test data, and we look at the error between the model and the actual observed consumption. This is purely, what I'm going to walk through here is just purely a linear regression model. It doesn't even have heating and cooling balance points. So this is not like a CalTrack model. I just want to use this as an illustrative example, but everything I'm going to show you is the math. It's quantitative. So when all I do is I say, I'm going to use an intercept only model. So the model is just telling, the model is only reflecting what is the average of these data points. Then I get a straight line that doesn't have any slope. And that model on the training data over here on this graph has a mean squared error of, say, roughly 18.2, thereabouts. And when I apply that model to the test data, the mean squared error is up around 19.5. Now, if I allow the model to be fit to the temperature, a linear model fit to the temperature, then this is what the model looks like. And I can see that I do a little bit better job in both the training data and the testing data at fitting this test, at fitting these data sets. So in both cases, training data and testing data, doing a better job. Now, if I also add weekend, weekday awareness to the model, I can see I do much better at this point. So certainly a lot of these data points that are a little on the higher side here are weekends. And a lot of the data points that are down here on the lower side of consumption are weekdays. And remember, I'm only fitting the model on the training data, and I'm using the testing data to give me insight into how predictive my model actually is. And as I add weekend, weekday awareness, I allow the model more flexibility. The model is able to split itself into two linear functions, and I get a massive improvement in the mean squared error of both the training data set and in the testing data set. Okay, so now let's also add seasons. So now I've added weekend, weekday, and seasons. So summer, shoulder, winter. So now the model has effectively 6 parameters. And I can see I still get some improvement in both the training data set and in the testing data set. All right, but why stop at seasons? Why don't I just say every month of the year? Why stop at summer, shoulder, winter when, well, September is certainly different than August. Why don't I fit August and September independently? So now I'm going to do that. And look at what happens. I get improvement in the model fit in the testing data set or in the training data set. So the data set that I'm actually using to fit the data, I still see improvement in the mean squared error, but the model has actually become less predictive. It's a worse model. So by increasing the complexity of the model, I have actually made it worse. And then if I take this even one step further and I say, well, now I'm going to allow the model to be fit on every week of the year, look at how much worse it gets. It gets way worse, even though it gets way better on the training data set. This is what's called overfitting. In this territory up here, I have an underfit model. If you'll remember, this was all the way back when the model just looked like this or this. The model is not complex enough. I need to add more flexibility to the model in order to make it fit the data better. And it's very advantageous to do so. But when I'm up here toward this end, I've actually made the model too flexible. It's fitting noise. It's not fitting actual underlying structures in the data. And this is the difference between an underfit model and an overfit model. Okay, so our hypothesis is that the CalTrack 2.0 daily model as it is currently formulated is an underfit model. It is not aware of weekend, weekday. It's not aware of seasons. And we see very definitive changes in consumption patterns between weekends and weekdays and between seasons. And so our hypothesis is most of the time, we need actually a little bit more of a complex model in order to get rid of seasonal bias, in order to get rid of weekend, weekday bias, and that we can do so and improve the predictability of the model. That's our hypothesis. But how do we diagnose this? And how do we find the right model components and complexity? And this is where cross-validation comes in. So I'm going to just walk through a couple more slides, and then I'll stop again for some questions, and then we'll keep going. So cross-validation. First concept to understand is that of test train split. And again, if you've been involved in a lot of modeling, this is all review to you at this point. And if you haven't, hopefully you're learning something new here, but these are all really core components because they're part of our decision-making framework. So test train split, I have a data set, let's say it has 100 points. Now I might take that data set and split it into 70 points that I'm going to train a model on, and then 30 points that I'm going to use as test data points where I'm seeing how well has my model at predicting data that it has not yet seen. And that's ultimately what's called test train split. Now, test train splitting has been around for a long time. So the model is developed on the training data set, tested on the test data set. This gives insight into overfitting, exactly what I talked about a minute ago. But it's very limited. There are issues with just stopping here. And there are better ways that have been developed over the last several years at actually formulating methods that you can use to gauge the predictability, underfitting, overfitting of your model. So this is what cross-validation is ultimately a more rigorous approach of more of a best practice. And in cross-validation, instead of just stopping at one training data set, one testing data set, you actually split your data into what are called folds. And you can have 2 folds, 5 folds, 10 folds. You have n number of folds. And in this case, Armin will talk in a bit about how many folds we're using and why. But in this generic example, every fold ultimately takes a turn as a test data set, where the other folds serve as a training data set, and you cycle through. So you're using all of your data and you're getting multiple test train cycles, which helps alleviate some of the bias that you can still wind up with if all you're doing is carving out one test data set. So you're effectively doing this over and over again so that you're smoothing out anything that would fool you by just doing this once. So this is kind of what this looks like. So you take in this case, you take folds 2 through 5. Those are your training data. You then test your model against the fold 1, which is now your test sample. And you do this 5 times. So now folds 1 and 3 through 5 are your training data, and you test that on fold 2 and so forth. And at the end of the day, you wind up with a model whose parameters and error profile are reflecting how well your model performed on the test data set. And you have independent verifications of that you've formulated with your starting data set. So ultimately, we have these 4 sources of bias that we know for sure exist: weekday, weekend, seasonal, thermal lag and behavior, and restriction to linear function. The solutions that we are proposing are to include a weekend, weekday flag, to include seasonal flags, to include thermal lag parameters that Travis will talk a bit more about, and the addition of a nonlinear term to allow for that more gradual onset of heating and cooling that we see around the balance point temperatures. But this is a lot of additional information. And so we're also using cross-validation as a way to make sure that as we add more parameters to the model, we're not just fooling ourselves, that we're keeping track of how well the model is performing at all times on test samples that we've carved out and are independent of the data that we've used to formulate the models themselves. So let me stop there and before I hand it to Armin, because Armin is going to talk a little bit more about how cross-validation is actually being formulated given the data that we're using to model. But this is a good stopping point to see if folks have any questions or thoughts or ideas for us as we're undertaking this. Okay, I'm going to take that as hopefully folks are on the same page here. These are complicated topics, So if you find yourself confused, don't feel bad. I was confused by a lot of this for a long time. Okay, Armin, I'm going to stop sharing and I'm going to hand it to you.
Okay, sure. Let me bring this here so I can take a look at it. Okay, can you see my screen?
Looks good to me, Armin.
Okay, great. So, first of all, my name is Armin Ali Gholian. I'm a data scientist at Recurve, and I want to walk you through to the cross-validation procedure that we have in order to find the best fit for the best model for the data set for individual meter data set that we have. Okay. So this here. Okay. So for now, let's look at 1 meter data set. And on the x-axis, you have the temperature. And as always, you have the observed value kilowatt hour per day in the y-axis. So we can, in order to define test train data set, we can obviously, as always, randomly some percentage of the data set and dedicate it as a train set, and the rest of it would be test data set. But in order to consider all of the distribution of the data that we have, we need to analyze different flags that Adam was talking about to enhance the model. One of the, I don't know why this doesn't work here. One of the flags or features that we wanted to consider in our train test dataset is the weekend and weekday flag. As you can see, we have 260 days in the weekend, in the weekdays, and 105 days as weekends. If you want to resample from the dataset, we want to consider these distinguished categories or segments in our dataset. And if you take a look at the seasonality inside of the this meter dataset, we can see it's pretty much obvious at the right side. With the higher temperature, we have summer, which means higher degrees, and we have basically in the mean value higher observed meter value for them. But if you want to consider all of that together, so which means weekend and weekday segment data and the seasonality on top of that, we will have a data representation like this, which means we have very few data points inside of each season's weekend. And we need to consider these segments weights in our resampling data to have a better and more realistic test data set compared to the trained data set. We want them come from the same distribution, so we can have a better estimate of the model error in general. Okay, sorry. Is that a question? Okay, no, I think that there's a mic on. Okay, so in the data set that I show you before in this picture, we want, in order to make the train test data set, we divide and sectionize the data to 6 actual segments. One of them is summer weekdays and all the way to winter weekends. But inside of each segment, we have a distribution of the temperature. So instead of randomly selecting from the data, which is uniformly resample from each segment, we bin the temperature and then resample from the bins inside of each segment. this helps us when we want to extract some trained data set. We have a better and more realistic representation of the whole year, same as for the test data set. And this these histograms that you can see you're watching right now is from 1 meter number 1 and k-fold number 1. What do I mean by k-fold? So we can have multiple train sets and test set together, and then sorry, I don't know if I can.
It's fixed. You can go on.
It's okay. I
Okay.
muted her. All good.
Okay, great. Thanks. So by k-fold means for each train test data set, we can train a model, and we will have a test error for each batch of train and test data set. But that will show one possible output for the error for the test data set. If we can resample the data again multiple times, which we call them k-folds, those folds, we can have multiple, we can train multiple models and assess the training error for all of them. And the mean value for those errors would be our expected mean value error for the new identically independent test data set that we will see in the future. For example, this one would be the next or another random sampling from the same structure of the data that we have. 6 segments, bins of temperature, and resample again from the same segments. And we can see other meters here. This is one of the k-folds that we have. As you can see, the train and test distribution is pretty much the same. They come from the same distribution in each segment. And we can see another random sample from the meter number 2.
So Armin, just a really quick point to connect the dots for folks here. So in every single case, the blue data is a training data set and the orange data is a testing data set from the very same model, or from the very same meter. I'm sorry, from the very same meter. So you develop a model on the blue data, you test it on the orange data. And we do this multiple times, which is what cross-validation brings to the table. So just to connect those dots.
Yeah, thank you. I forgot to mention that blue is train and orange is test. And so basically we follow a procedure that we normally use in the machine learning and is the cross-validation. But in this case, because we have the different classes or segments in our data set, which in our case is seasonality and weekdays, we have to consider those classes or segments in our resampling. We can do that like stratified k-fold, which all of those, each one of these columns that you can see here is one of the k-folds and the samples. And the red ones are the testing set, and the blue ones are training set. But it considered the fact that these classes weights inside of each training and test data set should be considered. We can't just randomly select. Oh, as a good example, if you have a time series data from January until December, if we train the data set on the first couple of months, first 9 months, and then test it on the rest of the day from September to December, we won't get a realistic error for that model. And another way that which we did is to shuffle the data while we're considering the stratified sampling as well, which that's exactly what we did, and it's great for imbalanced data set as we have here. Okay, so the first section we talked about how we can properly divide train and test data set, how many times we can do it, and how we will use it for model performance evaluation. But in this section, I went ahead and add those areas of bias that we have in the Caltrack daily as a feature to our model, to one of the model that I was analyzing in order to see the impact of these features, which later on we can use it in the actual Caltrack model. So one of the areas of bias were weekend and weekday, which we added a flag of 0 and 1 as a vector. And the other one is seasonality. We add these are the features that we're adding to our model. Seasonality, summer, shoulder, winter. This is the one hot vector for each individual point that we saw in the scatter plots that Adam and me showed in the previous slides. We consider the thermal lags up to 7 days before each day. And these are all on top of the base feature that we have for all of the models that we have. The base feature is the daily average temperature, which exactly the x-axis that I show you in the scatter plots. And the model that for now, I'll show the result of linear regression, but I've done some analysis on the neural net as well. But right now, I just want to focus on linear regression and analyze the impact of each one of those features that we added to the base feature, which is temperature. So in this slide, we see two figures. Let's focus on the left figure first, and then I'll explain the right side. They're basically the same but for two different meters. So in the y-axis, we have the mean error for each model that we train. And in the x-axis, we have the features, which starts from the base feature, which is T0, or the daily average of the same day. And then we add weekend weekday flag, which is W that I introduced, and the seasonality, and then temperature lag as we go forward. The red curve is the training is error for the training set, and the blue curve is error for the test set. And each point we see here, for example, this point here on the red curve, it's a mean value of 10K fold of the data. What do I mean by that? So again, the train test procedure that we explained, stratified sampling, we do that 10 times randomly. So we have 10 different train test data set. And for each one of them, we train a model, optimize a model on top of that, and we have an error for the test set. And we do that for all of those 10K folds, and then mean value of the errors is presented here. So as we can see, for this specific meter, we figure out that if we add the weekend weekday flag and seasonality and thermal lag up to 3 days here, we will get the best train error, test error for compared to all of other features, which means for this one, the analysis show that if we add these features, we'll get a better result. But in the next, in the right figure, we have the same error for, the same procedure we've done for the previous meter ID. We do that for this one, and then we saw just winter and seasonality, and the base feature, which is our temperature, is more than enough. And if we add more complexity to the model, more features to the model, it's not going to be useful for us. That shows for each individual meter, we will have different procedures. We should take different procedures, or we should introduce different features. In order to show a little bit more detail, I'll zoom in one of these samples, or one of these meter IDs. In the left side, again, we have as Adam showed before, we have the consumption in one y-axis and temperature in the x-axis, but the top model is for the train, for one of those k-folds, train data set and test data set on the bottom. So this one, the first figure on the left is when we just use the temperature. So it's a linear regression. We have a line. And when we add another feature, which is the weekend and weekday flag, we can see a little bit of improvement as if I can go back. As you can see in the orange triangles, the improvement is a little, it's negligible. But when we add seasonality, because we can introduce different complexity and different lines, we have a better estimation, which shows that this meter data set is completely reacted to the seasonality. And we have a better test and train error, and we have improvement compared to the previous one. And as we add more complexity, which is the thermal lag, to this meter data and the analysis and the procedure for the training and testing the model, we see the train set has a better error or lower error, which means we have a better model on top of the training set. However, we won't get a better test result for this meter. And as we can see, as Adam mentioned, this is overtraining. Overfitting, which means we have a better train error compared to the test error. And as we add more features, this gap will be more. Another data, same procedure, but this is another meter. And when we add more complexity to the model, we'll get a better result as we go forward. And for this specific meter, we have a better test error in general when we add up to 5 days of thermal lag. And yeah, so basically all of these analysis showed the first batch of the analysis was how we can do the test train as close as possible to the real data set that we have. So each train and test should be a good representative of the whole year and the whole data set. And after that, we implement different flags for the Caltrack error, the areas that Caltrack had error, and we saw for each individual meter, we should have a different solution and different feature set. So in order to get a better expected test error in for the future data set that comes in. And if you have any question about the whole procedure, train test and the model.
Yeah, I think we have a hand raised here, and before we do, there were also some good comments in the chat. So one point I want to make, and before we get right to these comments, is in this case, as Armin showed, if you back up, Armin, all the way to the beginning, when you went from like a unaware of weekend weekday to aware of weekend weekday, the model didn't have a big improvement. Where you had that example in here. So
here.
Yeah, in one of these examples, when you went from temperature only to temperature plus weekend weekday, the model didn't improve very much, right? On either the test or the training data set. I mean, it improved a very slight amount. But then when you incorporated seasons, it improved a ton. And if folks remember the example I showed, it was actually the opposite of this. It was when you incorporated weekend weekday into the model, you saw a dramatic improvement. And when you incorporated seasons, you didn't see much of an improvement at all. What is this telling us? Well, it's telling us that different meters behave differently, right? You have one meter that has a very distinct weekend weekday profile that's different from one another. You have another meter that weekend and weekday is about the same, but there's dramatic differences across the seasons, which tells us that for each of these meters, there's probably a different optimal solution. We don't need the seasonal complexity if it's not doing us any good. Whereas the other meter, we don't need the weekend weekday complexity if it's not doing us any good. Let's save those parameters for what actually matters. Now, somebody brought up a good point about using cross-validation with time series data. And of course, we're working with time series data here. But effectively, these data are actually not time series data in the way we are modeling them. Because all of the summer, for example, is grouped together. It doesn't matter whether the day is in June 2nd or September 30th. Those data points are treated the same relative to temperature. So it's not relative to it's not, they're all bucketed together in the same way. So they don't behave as time series data in the way that scikit-learn is warning about. So it's a good point. It's just to draw that distinction here. And I saw there was a hand raised. Abadun, did I say that name correctly?
Good enough. Hi, my name is Bjorn. I'm with VIC. Thanks. So the first thing I was going to talk about was the cross validation with time series thing as well. Because I think it's Lawrence Berkeley Labs. They looked at blocked cross validation where you have like a week, or if it's 15-minute data, you'd actually put days together or weeks together. And in this case, since you're dealing with daily data, it would be like, oh, what would the difference be if you group the data by week and you actually train the model across, basically it could actually be an entire year, right? But you stratified that year by those different blocks you've identified. So each pass or each segment would have all the different seasons represented, and weekday, weekend, and all that, and so on. And you did those splits, use those types of splits in your cross validation. It'd be interesting to see, would you still end up getting the same results as well? Because you made a good point that since you're taking the whole season together, right? So basically you're fitting a summer model and a shoulder season model, and and you're testing each of these individually. But if we expose the model to the whole gamut of data, but in a stratified way, what would the difference be? And then the other thing that I also wonder is, as you add features, how does the order in which you add features affect model performance, right? So in some of the examples we've seen right now, like, okay, say maybe you add, if we change the order in which you added, say, weekday, weekend versus your lag features, how would that affect model performance, right? It may be that overall the effect is the same, but if we did that randomly, would we notice anything different? And then my last point was looking at a bunch of this data. It just shows the power of having a model that is able to fit nonlinear relationships to the data, right? It's so clear in this chart I'm looking at that you just see that U shape, and trying to fit that with the linear model is, it's a losing battle.
Oh yeah, without a doubt.
Yeah.
I think that's really good. So tons of really good points there. Just on that last one, it's just to say we're using these linear regressions here as illustrative purposes, and Travis can talk a little bit more about like the real model formalism that we're investigating for the actual CalTrack model, but it's a very, very good point. And Travis, do you want to take a crack as you get into some of your slides at the points around like introduction of features at different steps in the process, like weekend, weekday, before summer, shoulder, winter? Because I don't want to speak for you, but I want to say like some of that is kind of built into how you're formulating things. If I've stuck my foot on my, that may not be true.
So I have not actually explored those independently. I've explored other features, which I'll show. But here going forward, that's probably a good thing for me to be checking independently as well.
Yeah, that's a really good piece of feedback. Maybe Abadun, do you mind if we reach out to you just kind of offline? I feel like this is a conversation we should nerd out on a little bit deeper.
Happy to.
Awesome. Thank you so much for that. That's really good feedback.
You're welcome.
I just want to add one more thing on top of Adam's comment. We use neural network to unfold those nonlinearity. We got a great result, but we have some calculation time and those type of problems. And in general, CalTrack should be interpretable. So that's why, first of all, we will show the result in the next meeting. And we'll talk about the limitation and advantage of neural network as well.
Okay, and Armin, I really appreciate the work you did here. It's really cool to see, and how you laid it out was super helpful. And I know I agree with you. I think with neural networks, they're super powerful, but the interpretability is not the best. And you know, just throwing this out there, like gradient boosting machines are like, I feel like a good middle ground where you can get some model interpretability on top of that, but it's also you don't have so many knobs to you don't have as many knobs to tweak as with a neural network.
Yeah, definitely I'll consider XGBoost and all those category of the models.
Yeah, thank you so much. And these are all things that we can consider as well as we get into CalTrack hourly too, because we're starting with CalTrack daily here, but CalTrack hourly is something that we want, that some of these considerations might be even more important. So let's keep these things on the table. Let's take one more question, and then I want to make sure we have some time for Travis, because there's more to get through here that we want to convey and get feedback on. Shay, what do you have in mind?
Hi, good day. First of all, I don't know what happened. My name is not Shay. My name is Shankar Ramharak. I think okay. The Zoom. I think something with Zoom kind of messed up our names, and it's been a mess. I genuinely apologize for that, and no offense to whoever was supposed to actually have this name. Secondly, I had some comments about the model, and before I continue, I'm trying to speed up here because I know we're short on time. I'm an undergraduate at the University of the West Indies, and I'm actually very new to this working group. I visited my first session, and I'm just catching up to speed on some of these things here. But the first glance, and based on the time series problem, which I have some background on, I wanted to know why isn't it that we use linear regression, right? Why is it that you didn't consider something like possibly spline, or maybe a spline with regularization, of course, or perhaps even if you were to use a neural network, make it much more interpretable by using differential equations as the weights, or rather even something as a physics-informed neural network, gearing more towards some of the approaches used in SciML. I'm sorry if that's a lot to unpack. I'm just trying to,
No, super good question. Travis, can we kick that to you?
Yeah.
So we actually have looked at more than just a linear regression. So we really approached this from two directions. One was that we largely wanted to keep the general model structure the same in my model. So this way we would be able to still get parameters that would be useful outside of just modeling, such as cooling load or heating load. Now, what Armin has been working on primarily is what are the limits, so neural nets, and he's also worked from the other direction of how simple can we make this, so multiple linear regression in this instance, and he may advance that further since we can see the limitations of that. He may advance that further in the future. But basically, Armin's approach to this is not so much like how can we interpret the model, it is how predictive can we make the model. And if CalTrack 2.1 ends up splitting the model between one is extremely predictive and its entire purpose is modeling, and the other purpose of my model would be to be able to back out this secondary information, we would consider this a success.
So upshot is the CalTrack model itself is not going to just be a linear regression across the whole shebang. And Travis is working on what is ultimately going to become, hopefully with everybody's blessing and feedback, the CalTrack 2.1 model. And so don't be confused by what we're presenting here, because what we're presenting here is more an exploration of where you start to get overfitting, and the and a validation of the cross-validation test train paradigm that we're putting in place for this project that we can take to using in the CalTrack model development itself. So hopefully that helps differentiate kind of what we're looking at now versus what we're actually considering as like CalTrack model formulation. So with that, I think it's a good time to transition into Travis. And Armin, would you mind stop sharing and we can hand the baton here?
Mute myself. All right. So can everyone see? We're good? All
That's
right.
good.
So I'm going to start off with a review, just so to catch everybody up who hasn't been around, as well as to refresh people's memory. So one thing that I've been looking at is one way to address the difficulty in being able to match different seasons. One approach would be to try to throw everything into one model. The other approach is to segment the data and to fit individual models to each of these segments. I'm going to be using splits and segments kind of interchangeably. I just do it out of habit. So here on the left is an example where I'm showing a severe seasonal bias. So for example, by the way, same plot as usual, temperature on the x-axis, energy usage on the y-axis. So what I've shown here is like, what if we had a winter month that is showing a very linear trend with some reasonable amount of scatter to it, but then the meter starts to begin behaving entirely differently during the shoulder month, and then there's kind of a break before it behaves again differently in the summer month. With CalTrack 2.0, it would basically try to split the difference between all of these. Whereas what I'm proposing is that instead what we do is we fit individual models to these seasons. Now, what I've shown here are linear models, but it would not be limited to linear models. It would be allowed to go up all the way to a 7-parameter kind of bathtub curve. Now, on the right side, what I'm showing is what would happen with a weekday weekend split. So at the top, let's say that this is happening on the weekdays and the bottom weekends. So this business basically, they just stop using energy during the weekends because they're closed. Traditional CalTrack 2.0 would try to split the difference between these two. Whereas if we actually split the data based on weekends, then you would get one model, which is largely temperature independent on the bottom. And at the top, you would get that traditional bathtub curve. Now, the question that then comes to mind is, well, how do you? We can't just split all of these separately because then that's going to be obvious overfitting. So how do we know how to split the data? My approach to this is to use model selection criteria, whether that be the Kaiki information criterion or the Bayesian information criterion. It's up to kind of determination. This is more or less a hyperparameter that needs to be optimized. Now, that is dependent. The way that these work in general is that they want to minimize the error. However, that error is penalized by the number of coefficients. For example, if we're just looking at models, not the splits, this model up here, where I'm showing the weekdays, would have a heavier penalization than the temperature independent region because we have more coefficients to describe this. What we can then do is we can add in an additional penalty to kind of be determined, though we've narrowed in on a bit of a region where we think that we're getting good results, where we penalize segmenting the data as well. So then the way that what we put into the AIC or the BIC is the number of coefficients as well as a penalty. So now the next thing to review would be the adaptive loss function. So CalTrack 2.0 is based off of ordinary least squares regression. There is the possibility that perhaps a better use or a better way to approach this would not to be to just look at sum of squared errors, which is what ordinary least squares regression is, but to instead allow the penalization to be adaptive. I'm not going to go into too much detail here, but basically, what I'm showing here on this top plot on the left is the loss response versus the number of standard deviations from the mean. It's a complicated graph, but we can simplify this and just talk about what's happening as you get further and further away from the mean. So for standards for sum of squared errors, that value increases rather rapidly, which means that value is going to increase rapidly when you're summing all of these up. And so these outliers are going to be pretty significant. On the other extreme, we could look at a Welsh loss function, which basically says, okay, everything past 3 standard deviations apart from the mean, it doesn't make a difference. It's just the same value. So this massively downweights outliers. So, and then the function that I'm using is actually a continuous function between these two extremes. And I've shown a couple of lines here that are typically used. But it is continuous, and you could find any value in between these two. Now, ultimately, these get transformed to weights, which then get transformed into kind of the plot that I'm showing over here, that this is a characterization, where traditional ordinary least squares would be the gray line here, where it's being pulled down by these points here at the bottom. And if we downweight these points significantly, which is probably what would happen, then you would end up with a result where you end up with something more like the orange line, where it's going more through the data points. Whether this is a good thing or a bad thing, that's up for debate, but I think that the debate is best served not to be solved by us arguing back and forth, but to be solved by looking at numerical values to determine whether this is the right way to go or the wrong way. So another problem that we run into with adding all of these models, because remember, when we started off with CalTrack 2.0, there was just one model to fit. 4 models to fit. Different breakpoints or balance points, but regardless, now we're talking about doing many more models. In fact, in order to do the information criterion that I was referring to before for the model selection criteria, I mean, we would have to do every model, every possible model. Well, one way to improve that, first of all, better initial guesses, that's kind of standard. So is picking the best optimization algorithm and all of that. But you still end up with somewhere between 40, 50 possible combinations of components, where I'll define what a component is. For example, here at this top one right here, FW stands for full week, summer, shoulder, winter. So this model right here is everything combined together. The next model that I'm showing is where shoulder is separate, but it's still a full week. And then there's a full week for summer and winter. Then as you go down to the next model, the full week of shoulder is the same, full week of summer, full week of winter, there would be 3 separate models here. As you can see, there's some overlap where I've highlighted that each one of these models is actually fitting the same set of data the same way. So we can basically save these intermediate fits and then combine the components however is necessary for each model to find out which one is best. This reduced my my computation time. It was starting to approach minutes. I think it was like 3 minutes. It brought it back down to like 20 seconds. So massive efficiency increase on this one. Now, we can still go further than that, though. One way is if we look at the data. Again, I'm showing kind of a standard plot. This one is actually a real meter, where the diamonds are showing the weekends. They're also a little bit darker. Circles are showing weekdays, and purple is showing winter, green is the shoulder, and blue is the summer. So if you look at this by eye, you as a person could probably identify that there's a pretty distinct chance that all of the weekdays are, like, it's possible that might require its own model. However, how do we transfer that to the computer? How can we get the computer to see that we might need to investigate this? Well, my approach to this is to fit a 2D Gaussian to each of the data sets, or each of the possible data sets. So for example, this one is summer weekdays, this one is summer weekend days, and then we do that for each season. Then if there is ever not an overlap, for example, weekdays and weekends of the shoulder months do not overlap, then I say, okay, we need to allow this to be a possibility and calculate this. Now for seasons, every single one of the seasons has an overlap. And since they all have an overlap, I say it's not really likely that that we need to investigate separating the seasons because they all overlap. So they're all going to have probably the same model. Again, arguments to be made about how big we make these circles. really that's all about how many standard deviations that you want to extend. This right here, I think, is about 2.5. And it seems to be giving me a conservative result where basically there has not been a single model that I have searched where I did not give the more possibilities for it to search than the final result actually chose. Okay, now I'm going to jump into thermal lag. I apologize for going so quickly. I think I'm kind of running out of time. So thermal lag. The way that I've approached this is on this plot, I show temperature versus time. Now the outdoor temperature, this is a general concept of thermal lag, not as it's implemented, is that the outdoor temperature has some behavior to it, some structure. And the indoor temperature, because of needing to heat the house, the walls providing insulation, because of double paned windows and all of that, it takes some time for that outdoor temperature to reach the house. And so that causes some kind of a lag between when the outdoor temperature was high and when the indoor temperature was high, or not really what the indoor temperature is, but how much heating and cooling is necessary, possibly refrigerator usage and that sort of thing as well, between when the energy usage increases. So this lag term is something that we want to take into consideration. The way that I have done that is to implement this moving average system, where, for example, here I've shown multiple days. So this is 2 days before. Oops. This is 2 days before. This is 1 day before, and this is kind of the day of. Now, did it again. Now on the day, if the way that we would normally handle this is that we would just average the day of, and that would be the temperature that we assign to a given energy usage. But what we could do is we could kind of change this, and we say, okay, well, what if there's a lag term that is mu, and this lag term is allowed to be -3 or all the way up to 3 days? This would be a negative lag, aka it would actually lead and would allow buildings such as, say, a commercial building, it knows that a heat spike is coming, and so they pre-cool their building. This would allow us to see that. And then we also add in this other term, sigma, where that sigma basically defines how far we're searching. So in this example, it would be 12 hours because we're searching for 1 day, but this could go all the way up to 3 days, which would allow us. So basically what I'm saying is this model allows us to go 1 day of lag where it doesn't even see the current day, it just sees yesterday's temperature. It would also allow us to do a 5-day moving average where mu would be 0 and the sigma would increase to allow more of an average. So basically I could take in a lot of different possibilities. This is what that would actually look like. Because remember, we're not changing the y-axis at all. We're just shifting things in the x-axis. So basically, you can kind of see where each of these is matched up to its partner. And this is how we would approach thermal lag. Apologize, I don't have time to go into too much more detail on this plot. But this would be an example of -2 hours with a sigma of 12 hours. So into the fun stuff. I ran this on a subpopulation where the subpopulation was in the MCE territory, commercial, with those commercial buildings that were flagged as automotive. And I had 707 meters that each of these uses. Now, the details of the test train split is that it's a 10-fold test train split with a 20 to 80 test train split. So 20% of it is test data, 80% of it is train data. If I run this on Caltrack 2.0, by the way, this is the root mean squared error of the test set divided by the mean value of each meter. Take the average of all of that, and this is what you get for all of the meters within this population. So Caltrack 2.0 is much higher than every other result that we're seeing. The lowest, surprising to me, I actually want to do a little bit more digging into this. It could also be because it's commercial automotive and not something like residential. Lots of caveats here. But sum of squared errors with Caltrack 2.1 was the lowest amount of error. When I say this was brought up, this uses the possibility of all splits. So weekend, weekday, weekend, and seasons. In the future, I might split these up separately. When I say might, I will. I also looked at what if instead of doing sum of squared errors, we do L1. L1 is basically the summation of residuals with just the adaptive loss function, which looks to be the second lowest. Interestingly, including thermal lag is actually worse on this subpopulation. Now, remember, the thermal lag can actually pick that it wants the same exact average that we currently use, because it could pick 0 and 12, 0 being the current day and 12 being plus or minus 12 hours. But this is still worse in the test train split, because for the train set, it's basically probably, no doubt, it's assigning some sort of a thermal lag, whereas on the test set, that ends up being an overfit. So I find this to be quite interesting results that genuinely surprised me and that I want to look further into. However, we are now at the point where we can start providing subpopulation data, and hopefully I can export all of this once I get to that point, so that we can start showing plots similar to what Adam showed before. And with that, I will pass it off back to Adam, and hopefully if anyone wants to stay late, we can address some questions if there are any.
Thanks.
There's a question. There's a question. Was there any reason for picking automotive buildings?
Yes, there was. I flew past it. The reason why we picked automotive buildings is because we saw a significant amount of weekday, weekend bias, as well as seasonal bias. As in addition to that, we also saw this, that was electric data. We were seeing interesting kind of behavior in just the structure of the data. So we basically picked that as a test bed, but that's not going to be the final end all answer. That is just the start. That's why it's preliminary.
Yeah, we'll be looking at res, we'll be looking at other commercial sectors. And this gets back to one of our decision-making criteria that is on that slide we show every week with respect to the adaptability of a model. Does it work just for res, just in California? Those things are problematic. We need a model that can work on data where it's available, and that data is consistently available no matter the jurisdiction, no matter the sector. And we need to test it across multiple sectors and in as many different climate zones and regions as we can, and different meter types, so gas and electric. So look for a lot more population level results, and we'll start to dive into different areas to validate these things as we go. But I think we're at a point now where things are going to get very exciting, because we've established the cross-validation test train paradigm that we're going to use. We've put together the pieces that we think could be in a model, that should be at least tested to be in a model and could be optimized. And now we're going to start, the challenge in front of us now are to build the data pipelines and start to execute these models on larger data sets where we can get population level statistics and start to see systematically, are we reducing seasonal bias? Are we reducing weekend, weekday bias? Does the introduction of thermal lag parameters help in many cases, or only a slight few cases, and in other cases it causes overfitting? These are the things that we're going to need to get on the table so that we can make decisions about what the final model formulation, how it's going to start to take shape. So thanks everybody for sticking with us here. Just want to preview kind of next time around. I think we're very keen on getting some of those population statistics so we can start to compare, like I just mentioned, and see, are we actually solving these problems that we've been talking about? To start to do some of the tuning that needs to go into some of these elements that Travis and Armin have been investigating. More modeling. Now we just got to start cranking as well. And we also have some work that folks have done outside of Recurve on EE weather. And so we are anticipating a poll request on EE weather, and we're super excited about that. So thanks to those folks. And next time around, I think we're looking forward to diving into how EE weather can be improved and what we're looking at there. So we're super excited about that. And as Travis said, if anybody wants to stick around, ask questions, I think this is kind of, I'm hopeful that at least for CalTrack Daily, this is sort of the last meeting where we're going back and we're doing like super deep, extensive reviews, because we need the time, I think, for folks to give feedback on like the actual model development. But I think it's been well worth the time to put into some of the ground level, like, setting the foundation for like, what problem are we trying to solve? What are we seeing in CalTrack 2.0? And some of the basics of like how we're going to use test train and cross validation. So stop there. If, as Travis said, anybody has any extra thoughts, questions, we're happy to stick around. Okay, hearing none, just want to say thanks to
I
everybody.
think we have one question
Oh yeah,
from
please
Shay.
go right ahead. Yeah.
Again, that's Shay, Shankar. So about that, right? You said you will be switching from Zoom to Gmail for the next meeting.
Mhm.
How exactly would that roll out? Like, would it be that Shay actually sends us the updated meeting information, or?
Yeah, it's gonna come. Yeah, it should come from her, I believe.
Okay, that's one. And two, as I said, I'm relatively new to this. The data that we're using to analyze these spots, right? Is it openly available on the cloud anywhere, or?
No, I really wish it was, but we're looking at data from a couple organizations that have allowed us to use their data for these purposes, but have not allowed us to share them publicly. So that does create some headaches, to be sure. What I would say is, if anybody has code that they have written that they believe should be tested against these data sets, because you believe that you have a model that solves some of these problems in a way that should be tested against what we're putting together, we're open to that. Let's talk about it.
Because I would like to actually start experimenting with some ideas I have. I did some look at time series analysis before, and hence the interest. And I wanted to see what some of the models will look like when they perform on these data sets here. Because in particular, it seems that some piecewise solutions might actually be better enough, or even some networks that are informed through differential equations. And I wanted to try my hand at it, but I'm not really sure where to get data from or how to augment a data set to even start experimenting with some of these ideas.
Yeah, so I think, were you at either of the last two meetings?
No, this is the first one I actually got the proper invite to, because I saw that there was some cancellation and then there's a pushback. I honestly was confused by the scheduling of the last two meetings.
I don't blame you there, and sorry for that. I would recommend going back and watching maybe the recording at the very beginning of the last meeting, because that meeting we talked about how to file an issue. Like in the first meeting, there was like a GitHub overview. So I would refer you back to those recordings. And then if you feel like you can put in the time and effort on those fronts to try to plug into the way that Linux Foundation Energy desires these things to be operated and collaborated, then we're happy to, if in other words, just bluntly, Recurve is devoting a couple people's time to this, but we're not devoting like 10 people's time. So if you have code and you have reason to believe that like your approach should be considered, or we can modify what we're doing to incorporate elements of what you're doing and improve things, we're open to that. But we need that to be pretty far down the road, like not time wise, but like we need it to be fairly well developed. Otherwise, it's really hard for us to just take a bunch of code and like try to figure out where it fits, right? So, if you feel like you have something and you want to, and you're willing to put in the effort and like get it to that point where we can plug it in a way that suits our system, we're happy to spend the time and like work with you and talk with you about it. So I'll just put that out there.
All right, no problem. Thank you very much.
Yeah. Great.
Shankar, depending on like how complex these model formulations that you have are, if they are relatively easy for me to implement into my existing structure, that's something that I'd be happy to talk with you about. Obviously you'd have to have some work done on if you're doing differential equations, then like what ODE solver you're using, like have all of that set up. But if it's kind of a plug and play model, it might be something that I could implement sooner than later.
Yeah.
All right, well, no problem.
So-
I guess I'll try and gather my resources properly, review them. I guess I'll get back to you probably offline or something. Do you have like an email or something I could continue offline with, or?
Yeah, if you can, I believe we should have your email if you've registered.
Yeah, but the
So-
thing is, the fact that I'm logged in as Shale Lindley here, I'm confused as if you would send to the correct person or what is going on exactly with the sign-in system. I can just drop mine in the chat, and you could just go from there if anything.
Yeah,
I put my email in the chat if you want to copy that.
yeah. Reach out and let's figure out if there's a path to follow here. Awesome. Thank you for that, by the way. That's exactly the kind of contribution I think we're keen on accepting and trying to figure out if it will improve things. Okay. Thank you, everyone. We'll call it here. Everybody have a great rest of your Tuesday, and we'll see you next time.